My name is Erran. I think it's good to come after Haifeng and Gentile. As you can see, it's going to be really sort of aligned with what they're talking about. So today I'm going to talk about reasoning foundation models for molecular world. It's an ongoing collaboration with my Stanford collaborators. And if you look at the current foundation models, there are two types of foundation models. There's these general purpose models like GPT and Claude. And so they're great. But if you give the model some structural understanding problem of protein, they're actually not able to understand the structure. So they may give you correct answers, but most of these just remember the answer from the training data. Right? If you give a novel protein, you ask them any structural questions, are out of luck. Right? So then if you look at some of these specialized foundational models like Chi2, alpha diffusion, or even specific models like AlphaFold, and they solve specific tasks, and then they're not able to generalize. If you give a harder problem, it's not able to reason about it. It's not able to leverage quote unquote adaptive compute, right? And so these are the limitations. And then I think I see there could be a paradigm shift. I think in my view is that for the first time, we have models that are truly intelligent, and could we actually leverage all these intelligence, these reasoning, and to actually help the molecular world, right? And then design these drugs, antibodies, for example, and small molecules. So, on a high level, we have a vision we call think proteo. Essentially, if you, it's just like human scientists, right? So, when a human scientist give a task, for example, we want to design a binder that binds to the SARS-CoV-2 spike receptor binding domain, and want to block AC2. That's the question. And then the human scientists look at the protein sequence and protein structure, and they start really contemplating, you kind of have a chain of thought. And, I'm not a bio person, but, we have great collaborators. And then, so there was some of the reasoning treatises, very reasonable. And then, and then once you sort of have a high level understanding, like, hey, what the structural constraints were at a particular spot, there might be a key residue that should stabilize the structure. And then with this, and then we have a diffusion model that's really sort of the design model that's trying to really design the binder, right? So, as you can see, you can leverage reasoning and then adaptive compute. It can sort of bridge the gap and generalize out of distribution. And so, we made some great progress. Hopefully, we're going to release something soon. But I think I want to highlight challenges. And so the reason that these frontier models hasn't really solved this is that they're really a big data challenges. There are limited amount of data, actually. The abundance of protein sequence data, but like structure data is only 200K, right? And then if you want to do reasoning, where are your train of thoughts, right? So, like if you talk to these bio experts and, they have some thinking process, but they typically don't write about it, right? And also model architecture. So because of the limitation of data, you can't really sort of brute force scale it up like the large language models. And there's a reason that AlphaFold designed all these inductive biases, this sort of evolutionary information like the sort of, the sequence similarity, right, the MSA, and then also the paraformer that encode a lot of these sort of biases in structure. And so how do we actually move forward, right, with new architecture that can do design, right? So, and then also evaluation, back to sort of what Gentile talked about. Sort of, we want to try to do more in silico evaluation, simulation, for example, have a world model for the molecular world, right? How does that look like? So eventually we will need to do wet lab, right? And then, yeah, so they're kind of really exciting for future directions. And so we want to sort of close the loop with RL-driven optimization using both computational rewards and maybe rolling out in the sort of world model, right? World model for molecules, world model for cell. People are really very excited about the virtual cell sort of direction, and also experimental validation, right? That with a lab in the loop kind of optimization. And eventually we hope to be able to, have systems that are really self-improving, right? Just solve all kinds of drug design problems. Yep, that's my talk. Yeah, thanks.